Welcome back, students, and probably this will be the last lecture for the syllabus of BTech first year Mathematics First. And in this lecture, we will learn the divergence theorem. Sometimes it is also known as Gauss Divergence Theorem, and some authors refer to as Gauss theorem. So let us start with the statement of theorem, and then we take some problems so that you can grasp the concept easily. I will not give the proof of the theorem here because this is not in your course, but if anybody require, I will prepare a separate lecture for the proof and upload it. So let us start. The Gauss theorem states that if v x y z, a vector function, and its first order partial derivatives are continuous throughout a volume bounded by some closed surface S, then the surface integral of the V over the surface S is equal to the volume integral of divergence of V. Means we have normal surface integral v dot ds as we have done in Stokes. Then we can evaluate this integral over the entire volume bounded by the surface S, and for the divergence of B. So in a short way you can say, if you have to integrate this v dot ds, this, then simply first find the divergence of V and evaluate it on the whole volume. So how does this take place? I have a figure here to make it easier for you to understand. Suppose you have to integrate over the surface of this sphere. So sphere is closed and this has a volume. This has bounded a volume. Now if you have to integrate some vector on this spherical surface, then alternatively you can take the divergence of the vector and integrate throughout the volume of this sphere. Here two things you must remember: that first thing, that surface in the Gauss theorem is always closed. If a surface is bounding a volume, it is always a closed surface. If surface is not closed, you cannot apply Gauss theorem. Second, the ds vector that I have written here is just n cap ds, and n cap is unit normal to the surface, outward drawn unit normal. We have learned in previous lectures. And divergence v is just del dot v. We have obtained in many lectures. And dv is written as dx dy dz as infinitesimal volume. So let us take some problems to get easy understanding of this theorem. Let us take our first example, and this is if V is a given vector x cube I plus y cube j plus z cube k, then the question requires you to evaluate the surface integral of this vector, and the surface is the surface of cuboid bounded by coordinate planes, and the planes x is equal to a, y is equal to b, z is equal to c. So let us first draw the plane and cuboid. Though it is not needed, this is very simple integral, but I am drawing that. So let this be looking like the cuboid that you need. Suppose this is our y-axis, this is z-axis, x-axis, and this is z-axis. So according to the question, this point means, and this is origin. Suppose this is A, so OA has the length A, so this has length A, this, and if this is B, so OB has length B, so this side has length B, and if this point is C, then OC has length C, so this has length C. So this is the box type structure, and you have to integrate the given vector on this. So let us start. I is equal to surface integral v dot ds, and Gauss theorem enables us to write this as volume integral of divergence of V, then dV. dV is volume. So first we need to calculate divergence of V. So we have already calculated a lot of, we have done a lot of questions for divergence. There is a separate lecture for this. So del dot V is equal to 3 times x square plus y square plus z square. And what is dv? dv is dx, dy, dz infinitesimally small elementary volume. So now in these terms, I becomes 3 times the volume integral of x square plus y square plus z square d z dy dx. I have written in reversed order dy dz dx by the special purpose. So let us put the limits. You can see this is a rectangular box type structure. So limit of x is 0 to a, 0 to a, and limit of y is 0 to b. This is 0 to b, and limit of z is 0 to c. This is 0 to c. I have written dz dy dx this because we need to follow the order of these limits. So I want to put these limits in order to look like ABC. So therefore I have written dz dy dx. Now you can integrate in any order. You can integrate z first, you can integrate y first, you can integrate x first. So let us integrate with respect to x first. So what does this give? This gives 0 to b, 0 to c, 1 by 3x cube plus y square plus z square x, and the limit applies to it, that is 0 to a dz dy. You can put these limits and again simplify it. So this becomes 0 to P, 0 to C, and 1 by 3 a cube plus y square plus z square a, and dy dz dy. Now continue integrating, and let us integrate now with respect to y. So we will get this 0 to c, because limit of y is 0 to b, that will be consumed here. So a cube by 3 plus z square a. I am taking these terms together because these are not the integrand for y. So this y, and then 1 by 3 ay cube, 1 by 3 ay cube. So whole limit applies 0 to b, and dz is remaining. Now again put these limits, and you get 0 to c a cube by 3 plus z square a b plus 1 by 3 ab cube and dz. Now you can integrate with respect to z. This is not tough. So just integrate and put these limits. So you will get a cube b plus b cube a c plus abc cube. This is our integral, and we have evaluated using Gauss divergence theorem. Now take our next example. So you can see the question, V is a vector given by 3xi plus 4yj plus 5zk, and we need to evaluate the surface integral V dot ds over the surface of the square x square plus y square plus z square is equal to 16. So this is a sphere, and I am not going to draw this. I am just first starting the solution process. So let I, we write the integral as I, this surface integral V dot ds, and ds means n dot d n ds, you know. So Gauss theorem enables us to write this as Gauss theorem, Gauss Divergence Theorem. This enables us to write the given integral as volume integral del dot v dv, and dv is dx dy dz, you already know, but first we need to find del dot v. So del dot v is divergence, and this can be find easily. So this is 3 plus 4 plus 5, and that is equal to 12. So in terms of this, we have I is equal to the volume integral of 12 dv, and this 12 taken can be taken out. So this is volume integral dv. And what is actually volume integral this dv? This is actually the volume. So this is 12 times volume of the sphere, x square plus y square plus z square is equal to 16. This is actually the volume of this sphere. So you need not even integrate, you can directly write the volume because you know the radius is 4. So this is equal to 12 times 4 by 3 pi, and cube of radius means 4 cube. So you can simplify this 1, and this 3 will cancel in 12, and nothing else will cancel. So we have 1024 pi. This is our integral. And let us take our third example. This says evaluate the surface integral of del x square plus y square plus z square ds, where S is any closed surface. And keep it noted that this question says any closed surface bounding a volume V, means there is a surface and which has a particular volume V. So let us start the solution because this question does not have sufficient information. So let I is equal to double integral S delta 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 x square plus y square plus z square dot and ds. This ds vector is written as nds. So Gauss theorem enables us to write this in the terms of volume integral. But before finding the volume integral, let us suppose, let phi xyz be denoted as x square plus y square plus z square. Therefore del phi is 2 times xi plus yj plus zk. So now we can write this integral in terms of phi as the surface integral of del phi dot n ds. And because del phi is a vector quantity, this is a single vector quantity. So using Gauss divergence theorem, you can write this as the volume integral and del dot del phi. This is a single quantity, so del phi and dv. Now we need to calculate del dot del phi. So here you can calculate easily. Del dot del phi means divergence of del phi. So this will become 2, 1 plus 1 plus 1, this is 6. So what you get is triple integral over the volume 6 dv, and this is just 6 times triple integral dv. And what is this? This is the volume of the closed surface S. So it is given that volume is V, so this is just our 6V. So you can mark that Gauss divergence theorem simplifies the work up to a remarkable point. Let us take our next example. It has a vector 4xi minus 2y square j plus z square k, and the problem requires us to integrate this vector over the surface of a cylinder bounded by the circle x square plus y square is equal to 4 and two planes xy plane and plane z is equal to 3. So this circle is just bounding circle of the cylinder, and these planes bounds the cylinder from bottom and top. So let us draw the cylinder. Let this be the cylinder that we are talking of, and this is x axis, this is y axis, and this is z axis. So this height of this cylinder is 3, and this is circle is x square plus y square is equal to 4, means circle at center with radius 2. So this is our cylindrical structure, and now we will solve the problem. So let us write the given vector as v is equal to 4xi minus 2y square j plus z square k. So first, the surface integral of v is given as, I am writing it as I, surface double integral over the surface of cylinder, this v dot ds, and Gauss theorem enables us to write this Gauss divergence theorem enables us to write this integral in the form of volume integral del dot v dv. So let us find del dot v. What is del dot v? So del dot v is just 4 minus 4y plus 2z. This is our del dot v, and dv, you know, dv is dx, dy, dz. So just put these things in the integral. So we have integral I, this is equal to the volume integral, and del dot v is 4 minus 4y plus 2z d dz dy dx. And what are the limits? So limit of z is 0 to 3, this is pre-specified. So and I am writing this as dx dy dz. So dx dy dz. So limit of z is pre-specified, and limit of x and y will be obtained from this circle. So I am leaving holding these limits as x on xy plane for some time. So you can see that z, limit of z has nothing to do with the limits of x and y, means limit of z is totally independent. Let me write actually, otherwise you may get confused. So limits of x can be written, and let me draw the circle again. This is this circle, x square plus y square is equal to 4, and this is x axis, y axis, x and y. So x square plus y square is 4, means the radius varies from -2 to 2. So the radius varies from -2 to 2, and then means x-axis varies from -2 to 2, not radius. So x-axis, x value of x varies from -2 to 2, and the value of y. So you need to write a perpendicular strip, and this will take the values from minus square root of 4 minus x square to plus square root of 4 minus x square. So you can easily see that variable limit is purely in terms of x, means this is limit of y, and x has constant limit. So limit of z is actually independent of limits of x and y. So we can integrate z independently. So let us first integrate this. So we get -2 to 2, and limits of minus 4 minus x square to square root of 4 minus x square limits of y and integrate z. So we have 4 minus 4y into z plus z square and apply the limits. Limit is 0 to 3 and we will have dx dy. So now simplify this and we will get I is equal to I is equal to double integral this minus 2 to 2 and this minus square root of 4 minus x square to plus square root of 4 minus x square. This is 21 minus 12y dx dy. So there are two ways you can integrate with respect to y directly, or it may become easier to integrate in polar coordinate. So let I am taking this in polar coordinate. So let x is equal to r cos theta and y is equal to r sin theta. You already know that dx dy become r dr d theta and radius varies from 0 to radius of circle is 2, so 0 to 2 and theta varies from 0 to 2 pi. So put these limits. So we have 0 to 2 as radius and 0 to 2 pi for theta. This is theta r is equal to and theta is equal to. So this is theta and r. Then put the values of x dx dy. So this is 21 minus 12 r sine theta and r dr d theta. Further you can observe that sine theta upon integration this will give cos theta and cos theta is same at 0 and 2 pi. So cos 0 and cos 2 pi will cancel each other, so this term gets 0. You can integrate and feel the actual result. So the content remains with us is just 0 to 2 21 r dr d theta. So and 0 to 2 pi, 0 to 2 pi. So 0 to 2 pi means you can integrate theta, so it will give 2 pi. So we have 42 pi 0 to 2 r dr. Now again you can integrate with respect to r, so you get this 84 pi. So this is your result and you further you can again see that Gauss theorem simplifies the things up to remarkable extent. Now let us take our next question. The vector v is given by r square I plus j plus k and r is the position vector xi plus yj plus zk. Then we are required to evaluate the surface integral of v over the surface of a tetrahedron bounded by the planes x is equal to 0, y is equal to 0, z is equal to 0 and a plane slant plane x plus y plus z is equal to 2. N is the outward drawn unit normal to the surface of the tetrahedron. So let us first draw how this tetrahedron looks like. So if this is the x-axis, this is the y-axis, and this is z-axis. So this plane x plus y plus z is equal to 2 intersects x at 2 0 0 intersects y at 0 to 0 and intersects z at 0 0 2, means two length on each of the axes. So this is how our tetrahedron looks like. This is the origin. So this tetrahedron has four faces, a front face and three faces on this face on xz plane, this face on yz plane and this face on xy plane. These are triangles and a final triangle that is looking in the front face. So you have already done a lot on this type of structure. So let us start finding our solution. So I is given as the surface integral. We are assuming it I v dot n ds, and Gauss divergence theorem allows us to write this. Gauss divergence theorem allows us to write this integral as volume integral of divergence of v dv. So now we first need to find del dot v. Del dot v is del dot v. This is actually, you can see that del r square by del x plus del r square by del y plus del r square by del z. And you already know how to deal with this type of partial derivative. So this is 2r del r by del x plus 2r del r by del y plus 2r del r by del z. And you already know that r is given by xi plus yj plus zk. This is already written in the question. R is given by xi plus yj plus zk. So r square is equal to x square plus y square plus z square. And we have discussed it many times that del r by del x is equal to x by r, and del r by del y is y by r, and so on. So we get this 2r x by r and 2r y by r 2r. So you can see r will get cancelled. So we just get 2x plus 2y plus 2x plus 2y plus 2z, means 2 times x plus y plus z. This is our divergence of v. Now write this into the integral. So I becomes this triple integral, and 2 can be taken outside, on the volume of tetrahedron x plus y plus z. And dv, this dv can be written as dx dy dz. So now just put we will just put the limits. So let us put the limits. So again I am drawing the structure. this this is your z-axis, this is your y-axis, this is x, y, and z axis. So this was how the tetrahedron looks like. So the front face has, this is origin, this is 2, this is 2, 2 intercept on each axis. So this has the equation x plus y plus z is equal to 2, x plus y plus z is equal to 2. So we first need to put the limit of x, then we will put the limit of y, and then we will put the limit of x. So for limit of x, just take the 2D diagram. This is x-axis, this is y-axis, and this is 2, this is 2. So equation of this line, slant line, x plus y is equal to 2. This is origin. So you can easily see that limits of x varies from 0 to 2. Then for the limit of y, you will take a strip in vertical direction, and you can find that limit of y varies from 0 to 2 minus x. And then finally limit of z from this equation, this one. So limit of z varies from 0 to 2 minus x minus y. So now in these terms we will write the integral. So I is equal to 2 times the limit of x taken from 0 to 2, then limit of y taken from 0 to 2 minus x, and then limit of z taken from 0 to 2 minus x minus y, and x plus y plus z. This is our integrand dx dy dz. So because the limit of z involves two variables x and y, we will first integrate with respect to z. So let us integrate it. So you get 0 to 2, 0 to 2 minus x, then x plus y z plus half z square, and the limit applies to this 0 to 2 minus x minus y dx dy. Now on simplifying you can get it as 0 to 2, 0 to 2 minus x, 0 to 2 minus x, and on simplifying the content of the integrand you will get 2 minus half x square, this is half, 2 minus half x square minus xy minus half y square, this, and dx dy. Now you can integrate with respect to y because y has the variable integral. So let us integrate with respect to y now. So I can be written after integration with respect to y as 2 times 0 to 2, then 2 minus half x square. This has nothing to do with respect to y. These are constant terms when integrating with respect to y. So this y minus x into half y square minus 1 by 6 y cube. So this whole has the limit of y means 0 to 2 minus x dx. Again you simplify this, just everything is 0 on the lower limit, so you just need to put y is equal to 2 minus x, and after simplification you get 0 to 2, 8 by 3 minus 2x plus 1 by 6 x cube, this dx, and now you can integrate it very easily, and that just happens to be 2 by 2 into 8 by 3x minus x square plus 1 by 18 x to the power 4. So limit is 0 to 2, and just see that everything is 0 again on the lower limit. So put x is equal to 2 as upper limit, and you will finally get 2 and 2 inside the bracket, so we have 4. So this is our integral, means the surface integral of this given vector integrated on the surface of the tetrahedron, but using Gauss divergence theorem we evaluated using the volume integral, and it is completely very easy. And finally, now let us take a question to verify the Gauss theorem. So we have a vector 4xz minus y square j plus yzk, and the surface that we will use to integrate for the surface integral, this is the surface of cuboid. This is a unit cuboid, means all the sides are 1. So let us start finding the solution. First we will draw the cuboid. So here is the cuboid, and though my graphics does not looks pretty good, but you must assume that I have drawn a cuboid, means all the sides are same, and this is z-axis, this is x-axis, and this one is y-axis. So these are all 1 1 and 1, every side is 1. So in terms of coordinate, this point, this is 1 0 0, this point is 0 0 1, and this point is 0 1 0, and this is origin, means 0 0 0. So now take I is equal to the surface integral, or you can say in language that surface integral of the given vector. So surface integral of V is I as double integral over the surface of cuboid and V dot ds. Now Gauss divergence theorem enables us to write this Gauss divergence theorem enables us to write this integral as a volume integral, V volume bounded by this cuboid, and divergence of V dV. So where we will find divergence of V. So divergence of V is very easy. You can find this is 4 times z minus 2y plus y means 4z minus y. This is the divergence, and dv we have discussed several times, dx, dy, dz. So in terms of these things, the integral I becomes the volume integral 4z minus y dx dy dz, and because this is a cuboid, so all the limits are 0 to 1, 0 to 1, 0 to 1. So these are all constant limits. You can integrate with respect to any variable first. So you can see that integrand does not contain x, so we may integrate with respect to x first. So integrating with respect to x first, we get 0 to 1, 0 to 1, and x 0 to 1, 4z minus y dy dz, and this is just 0 to 1, right in separate line. This is just 0 to 1. I is equal to 0 to 0 to 1, 0 to 1, 4z minus y dy dz. And now you can integrate with respect to z or y first. So let us integrate with respect to y first. So this is 0 to 1, then 4zy minus half y square, and the limits of y are 0 to 1. Now you can easily write this as 0 to 1. Upper limit is 1, lower limit is 0. So all the terms become 0 as lower limit. So this is just 4z minus half dz, and you can integrate it. So first term becomes 2z square and second half z, and you will get 3 by 2. So this is the result that we obtained this Gauss divergence theorem. But the question requires us to verify the theorem, means we need to obtain the same result without using Gauss divergence theorem. So let us start finding the same. So in order to verify the theorem for Gauss divergence, we need to take the surface integral on all these surfaces. So I was integral over S v dot ds, and that means integral over s v dot n cap ds. Now we will evaluate this on individual surfaces. So first start with the surface OEFA. So on this surface OEFA, we will start evaluating our individual surfaces. So on OEFA, you can see here Z is 0, and what is surface normal? Surface normal is this surface, this is plane xy, so its surface normal will go in below direction, means opposite of k. So this surface normal is minus k. So what we get, v dot n, v, you already know that v is the vector 4xz plus 4xz I minus y square j minus yz k. So what is v dot n? V dot n is minus v dot k. Why minus v dot k? This n is equal to minus k. This is n is equal to, I wrote mistakenly, this is minus k. So v dot k is what? V dot k is this. So look here, v dot k is minus minus yz, and because z is 0, so it is 0. So the integral I on this surface OEFA I1 v dot ds, this is equal to 0 because integrand is 0. this is 1. Now on the next surface we take the opposite surface. What is the opposite surface? This CDGB. So on CDGB you can see here Z is equal to 1 and unit normal on this surface is K. So again find V dot N. So V dot N just YZ and Z is equal to 1. So this is just Y. So integrate it and no, this is minus, this is minus yz, so this is minus, so minus y, and now integrate. Let us say this integral I2, that on the surface CDG P. So this double integral minus y, and on this integral c dgv x varies and y varies. So this is dx dy, and the limits are 0 to 1, 0 to 1 minus y dx dy. So after evaluation you get this minus 1 by 2. Now on the next surface number 3, on the surface OCDE means x is equal to 0 plane. OCDE, this is OCDE. So on OCDE normal will be negative of I and x will be 0. So x is 0 and normal is negative of I. So what is V dot N? V dot N is minus V dot I, because N is minus I, and that is equal to minus 4 xz, but x is 0, so this is again 0. So our integral I3 on OCDE V dot and ds, this is again 0. Now we take the fourth surface, means opposite surface to this, means this surface ABGF, 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 and here the value of x is 1. Normal is in the direction of I, so normal, unit normal is I, and V dot N, V dot N, what is V dot N? So this is V dot I, and V dot I means 4xz, but x is equal to 1, so we have just 4z. So write the integral I4 as the integral ABGF and V dot N ds. So put the limits 0 to 1, 0 to 1, V dot N is 4z, and what is ds here? So ABGF, you can see this ABGF. So here y varies and z varies. So we have dy dz. X is constant, x is equal to 1. This x is equal to 1. So on this surface only y and z varies. So this dy dz, and after evaluation we get this 4z, so z square by 2, so we will get 2. And now we evaluate on the rest two of the surfaces. So uh, on the surface we take OABC, OABC. So OABC surface, this is y is equal to 0 surface, this surface. So on OABC, y is equal to 0 and unit normal is minus j. This is the back surface, and this EFGD, this is the front surface. So along front surface, here is the unit normal j, and in the back direction unit normal minus j. So unit normal is minus j, and we take V dot N, this is equal to minus V dot j, and it comes minus y is minus y square plus y square. This is minus and this minus, so this become my y square, and because y is 0, so this is 0. So our integral I say it I5 the integral O A B C and V dot N ds, this is again 0, and the final integral along the front surface D E F G. So D E F and see on this surface y is equal to 1 and the unit normal is in direction of positive direction of y-axis, so this is j. So v dot n is obtained, we have already obtained minus v dot n, so this is minus y square and y is equal to 1, so this is minus 1. Now the integral I on the surface D E F G V dot N ds, this, so this double integral 0 to 1, 0 to 1, and v dot n is minus 1. And what are the variables that are varying on this surface? So here y is fixed, y is equal to 1, so x and z vary. This is the z, this is the x axis, so x varies and z varies, so we will write dx dz, so this dx dz, and we get minus 1. So now let us sum all the this is I6, all these I1 to I6 to get the integral. I is equal to I is equal to integral over the surface of cuboid v dot n ds. This was I1 plus I2 plus I3 plus I4 plus I5 plus I6, and we obtain the values minus 1 by 2 plus 2 minus 1, rest all are 0, so this is finally 3 by 2, and we also obtain the same value using Gauss Divergence Theorem. So we have verified Gauss Divergence Theorem for the given vector and surface. So this is the last question, and I hope I have covered the variety of questions. Now you can solve the you have many questions in different books you can solve, and if you have any problem you can put in the comment box. Thank you everybody, either you are my student or any other aspirant of mathematics. With this last topic, I am putting the series of lectures to an end. Actually, if all of my students already know, and if you are not my student, I should tell that the lectures were made, prepared for the students of BTech first year engineering mathematics first. So I have covered the syllabus, and therefore I am putting this to an end. But still, if you have any topic and you like the content, you can put in the comment box. I will prepare the lecture on the topic of your preference and upload when I get time. And the last word that I should tell all of you, that I have not economized my lectures, means I am not earning money. So if you see some ad during the lecture, this is purely from the Google and YouTube side. Actually, they do not deliver the content free of cost to you. They present ads and they earn money. So do not feel any time that I have any concern, special concern for anybody to watch my lectures. Your freedom, you watch if you like, you watch if you like, you comment, and nothing else. So finally, I rest my words here, and thank you very much.